This bridge is monumentally huge. Not this bridge, that bridge.
Deep in the south of France, the stunning Millau Bridge is a record breaker.
These tapering concrete giants are the tallest piers ever built.
From the top, you would look down on the Eiffel Tower. Driving above the clouds, you cross the longest cable-stayed bridge deck on Earth, spanning the deepest canyon in Europe. Each year, this spectacular engineering achievement faces extremes of wind and heat in a valley no one thought could ever be conquered. But it wouldn't be standing here today without the power of lightning.
$750,000.
What? A frying pan. A lost nuclear submarine. An accident in a silver mine. And a crafty trick of ancient Celtic boat builders.
How did all those make that possible? This triumph of engineering and design lies in the massive Central Mountains of southern France.
It was built to lift a curse on the tiny town of Millau. For 30 years, the auto route linking Paris to the beaches of the Mediterranean sped south through the French countryside.
Until it hit this, the Tarn Valley.
A 2.5-kilometre wide, 250-metre deep gorge, or in technical terms, a very big gap. To cross this gap, the tourist traffic was diverted off the 4-lane express route and funneled over Milau's tiny 2-lane medieval bridge.
Summer in Millau was a nightmare. Gridlock traffic with 3-hour tailbacks and 18-mile queues.
After 3 decades of mayhem, it was time to conquer the gorge. And so in 2004, the world's tallest road bridge was born. A giant span, 1/4 kilometre high. The final lightweight steel design was the engineering equivalent of a curved ball, because the road is not straight, it arcs as it spans across the valley. The bend, designed to keep drivers alert, meant that for the engineers, it was not going to be simple to build. They needed a complex skeleton of over 2,000 individual parts. Cutting that much steel quickly and accurately would mean they'd have to master one of nature's greatest forces. But first, to get the inside angle on the jigsaw of steel that makes up the deck, security have granted me special access.
This, in case you hadn't guessed, is the tunnel inside the deck. So right now we're sandwiched between the road up above and then, well, nothing below. And from inside you can see just how clever it is. It's hollow. They worked very hard to make it strong and light, and to do that they needed thousands of pieces of steel that had to fit together precisely in a massive jigsaw to make the curve of the deck. And each of those pieces of steel had to be made individually and in record time.
And there's the challenge. How to cut 2,078 giant pieces of shaped steel with incredible precision, phenomenally fast.
The traditional way to cut steel is with one of these, an oxyacetylene torch. It works, but it's not fast and it's not easy.
Painstakingly slicing over 2,000 steel panels with oxyacetylene was a potential nightmare for the engineers, especially with a €25,000 penalty for every day's delay if they went seriously over schedule. So for the solution to their cutting challenge, they harnessed the power of lightning. A bolt of lightning is an electric current that can generate up to 300,000 amps. That's enough to power 24,000 domestic kettles. More importantly, when a lightning bolt arcs through the atmosphere, it literally changes the world. It produces a new state of matter, and it's the key to cutting steel quickly. I'm about to see how. First, I'm going to control lightning. This machine belongs to a special effects expert. He's going to help me become a human lightning rod and direct a scary amount of power. Mark Turner is my lightning wizard.
Wow, Mark, this is like walking onto the set of a 1950s B-movie.
Do you like it?
It's brilliant, I think. What is it?
It's a lightning machine. It's what we call a Tesla coil.
Okay.
It produces lightning. What I'd like you to do is to put this on.
I'll get dressed up.
You do get dressed up. This is the fun bit.
That looks like chainmail.
It is chainmail. It's what we call a Voltrex suit. It'll
Right.
protect you from the lightning.
Okay, there's holes in it. So what are boots off?
Boots off, please. Check it off.
Are you entirely sure about what we're doing here?
What can possibly go wrong? Scarf off.
My best scarf.
Look after that, James. So 1 foot in there.
Nice.
It's just the right size, isn't it? So the machine outputs about 750,000 volts.
What?
But this suit will protect you.
It's got holes in.
It has got holes in it. Can I have your hand,
No.
please?
The metal suit will act like a cage, allowing the lightning to flow around me rather than through me. At least, that's the theory.
Just run it by me again, the whole, if the chainmail doesn't work thing, what happens?
If it were to go through you, that would be a bad thing.
When you say, let's not explore the badness of it, yeah, which is bad.
It's very bad. I mean, it's not instant, but I mean, your odds are against you rather than for you.
Thank you. Stop talking now, please, Mark. Don't say any other words. Oh, look now, I'm connecting to the metal.
The Tesla coil massively increases the mains voltage. When the energy level's high enough, current will flow to me, and I should be able to direct it with my finger.
What about screaming and going like that very quickly?
So, everybody with sensitive hearing ought to leave the room now. Anybody with implants in their ears or pacemakers or heart problems ought to leave now. And we're good to go. So, good to go, Richard?
I feel lonely.
Fantastic.
Mark takes a moment to build the voltage to lightning levels.
You feel okay?
This machine was conceived by eccentric 19th century inventor Nikola Tesla. Labelled a mad scientist, well, he fell in love with a pigeon. He was also a pioneer of robotics, radio and electric power. In the course of looking for ways to transmit electricity across America, he devised this way of controlling lightning. Like nature's lightning, my lightning wants to find the shortest way to Earth. It is the most extraordinary experience, like millions of ants crawling all over me.
Okay, crew, let's go in.
So I was making lightning come out of my fingers, briefly. It can't by some freak chance just continue to happen for me specifically.
Unfortunately, no.
That is a superhero movie I'm
It
thinking
is.
of, isn't it? Okay.
So controlling lightning looks good, but how does it help engineers who want to cut steel fast and precisely?
The answer to that is as fantastic sounding as lightning is to look at, because what is happening is the huge surge of electricity turns the air into a fourth state of matter, plasma. We're all familiar with three states: solids, like ice, liquids, like water, and then gas, like steam from a kettle. And we're all familiar with the way you move from one state to another. If you heat the solid, you get a liquid. If you heat a liquid, you get a gas. Well, if you heat a gas with, say, a huge surge of electricity, you get plasma, the fourth state of matter.
Plasma is actually common throughout the universe. The sun and the stars are pure plasma. But it's very rare on Earth. This is a slow-motion shot of man-made plasma. When it's controlled and super focused, its heat can be used to cut metal.
This is a plasma cutter. A stream of pressurized air comes out at the tip. That air is charged. That's what creates the plasma, and that's what melts through the steel.
Just as lightning charges air and turns it into a plasma, the electric current in the cutter does the same. It charges the air, turns it into a jet of plasma, and that's what melts the metal very quickly.
This is staggering, the speed. It's actually 3 times faster than an oxyacetylene cutter. But there's absolutely no sense, of course, of resistance. There's no effort to it from me. I'm just moving along the surface of the metal.
Plasma cutting is brilliant for big metal construction because it's quicker than oxyacetylene. It also creates a much cleaner cut, so it needs less finishing, and that speeds production yet further.
Just air and electricity doing that. The power of lightning.
Plasma cutting on a grand scale was the secret behind making the Millau Bridge road deck. Here at the Eiffel Metal Construction Company, yes, the same Eiffel that built the Paris Tower, the lightning heat of the plasma cutters sliced over 2,000 steel segments in just 2 years. So that's how the deck of the world's longest cable-stayed bridge was built, by controlling the power of lightning. But once they'd created the road deck, they faced another challenge: putting it in place without toppling the colossal towers built to hold it up. A lucky accident that reinvented the frying pan would solve this problem. The Millau Bridge engineers had to somehow launch their steel road across the top of the giant concrete piers. But to achieve this, they had to devise a radical new delivery technique.
On your regular bridge, there's kind of 2 main ways of getting the deck onto the piers. First of all, you build your piers, which I'm doing here with bread, obviously. There we go, that's my piers. Then you can either build sections of your deck actually on site and crane them into position, and there's my bridge complete. Or option 2, you can build the whole deck and push it out over the piers from the sides of the valley until it's in place. Perfect. But Millau is not your regular bridge. For one thing, because of the depth of the valley they're trying to cross, the piers are not little squat ones like these. They're great big tall ones like these, which means once they'd actually got these into place, 240 meters tall, the expense, difficulty and complications of using cranes to lift the sections of road bridge up were just immense. So you go for the second option. You build the deck, you push it out. But with piers this high, 240 meters, the sideways force of the deck would just topple them, and disaster.
This is the engineer's solution: a special hydraulic jack. It uses 2 giant, but over 15 months, the giant road deck was slid precisely and safely into place.
It's incredibly simple, but very, very clever. There's just one thing. 36,000 tons of decking are pressing down on top of these wedges. They have to be able to slide over one another to work. Well, to do that, the engineers had to rely on the most slippery substance ever created.
Back in 1938, chemist Roy Plunkett was working to improve the efficiency of fridges, but he ended up making an amazingly slippery powder. He'd made PTFE, polytetrafluoroethylene, known the world over by its famous brand name, Teflon.
New black, no-stain Teflon. Even hours after cooking, pans rinse clean in seconds. No soaking, no scouring. Teflon inside.
It really is the slipperiest thing made by mankind. Now that sounds like something that's got to be put to the test, which is where my friend Warwick comes in.
Right.
Well, when I say my friend Warwick, it's more...
Boris.
Yes, Boris.
Boris is a gecko. He's got the stickiest feet, I would say, in the animal kingdom.
This is Boris the gecko, performing for us the gecko test on a piece of glass. Well, that's Boris quite happily... There you go. That's vertical, maybe even a bit more, and that's glass gecko tested by Boris. Now we must test Teflon. So,
Right.
let's perform the gecko test. I've just realised this might be quite disconcerting for Boris, but Boris, don't think what I know you're now thinking. We're using frying pan because it's coated with the material, not because of, you know, the cooking thing. Okay. I'm sorry, Boris, I'm really sorry. But I wouldn't blame him if he jumped straight out of this. Right, so let's try him on this. Oh, not a hope. We can't. Well, clearly then our non-stick material passes the internationally recognised gecko test with ease. No, it's gecko-proof. I think that really is the final word from our gecko tester. Teflon really is very, very slippery.
Once the launch had begun, there was no going back. And PTFE proved itself on the wedges, sliding the massive steel road deck over the valley. All thanks to the wonder non-stick stuff called Teflon, discovered by luck in a lab.
Now the engineers had to face their next big problem. How to construct the tallest piers ever built, each to a specific point in the sky, with millimetre precision.
The highest of these giants is 245 metres, as tall as a 70-storey skyscraper. And the other 6 aren't exactly short. They all had to end up in exactly the right place, within millimetres.
They were only possible with the technology from the submarine war games of the Cold War.
Engineers analysed the stresses and strains on the bridge round the clock, 365 days a year.
This is the control room, where today cameras and sensors monitor the traffic, the wind, temperature and humidity. But back then, when the bridge was under construction, it was, if anything, under even closer scrutiny. Reflectors dotted about over the structure allowed the engineers to track the build and monitor the bridge's precise position.
The engineers needed to build each towering pier up to a precise point in space, hundreds of metres above the ground, so it could meet the horizontal deck as it slid out, thousands of metres from the valley sides. A precise surveying network ensured that they got to exactly the right point in space, to within millimetres, impossible without a supremely accurate system of measurement. The kind you'd need to find a dot in the ocean. Cue our next connection.
Question suivant, le 553.
It all started when US nuclear submarines began to get lost. The subs were designed to submerge for months, with gyroscopic systems to record every move. But over time, tiny errors mounted up.
When the subs surfaced out in the middle of the ocean, they couldn't work out where they were. A precision nuclear weapon is not much use if you don't know which way to point it.
The US Navy's solution was to launch satellites. On surfacing, the subs would listen for the satellite signal to work out where they were. It was the very first use of satellites for global navigation, the foundation of today's global positioning system, or GPS as we all know it. But how does it actually work? And how could a signal beamed from 20,000 kilometers away help engineers build a bridge to millimeter accuracy? The trick is to calculate how long a signal takes to get to Earth. If you know its speed and when a signal was sent, you can work out distance very accurately. To see just how this works, I'm meeting John Shelton, an expert in the field of acoustics. In a field.
Hi, John. Hi, Richard. Well, I'm here, and, well, frankly, I'm confused. So, first of all, how can you measure
these distances. What are we going to do?
Well, you know how GPS works. You've got satellites up in the sky that are beaming out signals down to us.
Yeah.
So depending upon where we are on the surface of the Earth, by measuring the delay between those signals from the different satellites, we can find out exactly where we are.
Because we know where the satellites are and we can measure the delay. Yes, I can get that.
That's right. The only problem is we haven't got any pet satellites. So instead of using radio signals, we're going to be using acoustic waves.
Noise.
Exactly.
Yeah, okay. How?
So what we need is a nice noise source.
I've got my car, I can start it up, it makes quite a racket, big V8.
No, I think we can do better than that.
All right. It's this. I did wonder. It's in here.
It's in here. Let's
Okay.
see.
Can I help? That's louder than my car. It's quite handy, isn't it?
Good enough?
Yeah.
We've got the gizmo over here, and we're going to take this with us, and we're going to be making the noise as we go down and measuring the delay as we go. You coming with us, Chris?
At 20 degrees centigrade, sound travels at 340 meters a second. By walking away from the truck, then stopping and playing some notes, we can measure the delay between the sound leaving the speakers back at the truck and reaching us. John's computer uses this time difference to calculate a distance.
Now.
Okay, let's try here.
Right, okay. Go on then. Take it away.
I immediately noticed the delay between Chris playing and us hearing the sound. Let's rewind and check that again. Chris strikes the strings, then there's a delay before you hear the sound from the speakers.
Take it away.
The electrical signal travels to the speakers the instant Chris plays, but it returns through the air at the speed of sound. When you get far enough away, the delay becomes quite obvious. John's computer measures the time it takes the guitar notes to get from the truck at A to us at B. From this, knowing the speed of sound, we can work out how far we are from the start. So a half-second delay would mean that we're 170 meters from the speaker stack, our own version of a GPS satellite.
This is quite weird.
Will that do you? 170.
There you go, thank you very much. So although what we've been doing was a bit, well, frankly, odd if you were watching from over there, probably, but we were using a signal to measure distance. And it doesn't matter what the signal is, we use noise, it could be anything. If you know how fast the signal is travelling, and you know how long it's taken to get from one point to another, then you can use that information to work out how far apart those 2 points are. You don't need a guitarist.
The satellite signal the nuclear subs listen for contained data on the time it was sent and where it was sent from. And the more satellites you have, the more precisely you can fix your position. Measuring the delay from the time a signal was sent to the time it's received, you can work out how far you are from a satellite, just like we calculated our distance from the guitar amplifiers. Today, there are 24 global positioning satellites orbiting the planet, sending signals back to Earth. Now, GPS receivers use exactly the same principle, only with greater accuracy. They compare the distance from 4 or more satellites to determine their position. Your GPS receiver can work out where it is to within 10 meters. That's fine for directing your car, but completely useless in building a bridge where an error of 10 centimeters would be a disaster. The Millau engineers fixed GPS receivers to the deck and piers to keep construction on track. Their system was way more accurate than car sat-nav, but it still wasn't enough. Tiny temperature fluctuations and building stresses could send the piers and deck off course, and although successfully guided by the satellite data, they needed to double-check their GPS.
The engineers took GPS guidance a step further. They bolted a receiver to a fixed point on the side of the valley, and it provided a reference signal for all the other receivers on the piers. Because it's anchored,
It reduced the error of the GPS signal down from meters to millimeters.
The network of monitors on the bridge constantly check the accuracy of their position data against these known points. And all the time, the towers climb skywards. So that's how a technology for locating lost subs positioned with pinpoint precision the world's tallest piers. But Millau's steel roadway, weighing 5 times more than the metal used to build the Eiffel Tower, needed support from above as well as below. And that's where cables come in.
When the deck was being pushed out over the top of the piers, the engineers used a web of cables to support the end of it, and they held it in place even when the winds blasted up the valley.
So how did 36,000 tons of steel road stay put in a valley notorious for storm-force winds? The answer lies with a series of accidents in a German silver mine. In winter and early spring, Europe's weather can turn on its head. Low pressure over the Mediterranean sucks cold air from the north down through the south of France.
The Tarn Valley is pretty much your perfect wind tunnel, channeling mountain storms along its length. Winds here can reach 130 kilometers an hour.
That's a pretty severe test for the cables here on the Millau Bridge. They take the strain, but it's only because of a series of mining accidents that they exist at all. Throughout history, miners have hauled heavier and heavier loads up from below ground. But this put dangerous stresses on the traditional pulleys and ropes used.
Man has made rope since the earliest times, and depending upon where you lived, you could choose from a range of different plants to make it. In Asia, a relative of the banana plant was used to make manila. And then across much of Europe, cannabis, of which this is a relative, was used to make hemp, amongst other things.
Rope is usually made by twisting fibers together.
But it does have its limitations.
To understand rope's limitations, I've decided to break some, and materials expert Clive Sevier is going to help me.
Okay, Richard, what we've got here is a hydraulic press with a load cell here.
Yeah, okay. So it's going to pull on there.
Yep.
And this.
That's going to tell us the force that this is supporting.
And this is rope as was used initially in the silver mines and well, everywhere else. I'm going to start the machine by pressing, I'm guessing, the big green button.
Taking up strain.
Right, so we're just starting to stretch the rope now.
This is a 10mm hemp rope, about the thickness of my little finger.
Now we're just starting to increase the load. We've just hit 30 kilograms.
30. Oh,
the rope is stretching a lot, as we call it, yeah. And here we go, the load's increasing. We've just hit 100 kilograms, 200. And we're now on 260 kilograms. Yeah. And now we're just hitting 300 kilograms.
And it is stretching. Oh, there you go, look.
And there we go. The rope doesn't break suddenly, but it gradually, different strands of the rope start to break individually. It's still supporting some load until eventually the final strand will break.
And that's your lot.
Got to 640 kilograms.
That's nearly 2/3 of a ton.
So the way it breaks is useful.
That's right.
The weight at which it breaks is not so good.
The rope breaks gradually. Single strands break, but the rest of the rope still holds some of the load. And so it doesn't sort of just give up.
So we need now to test something.
Exactly.
To earn more, the miners needed to haul bigger loads, so they were looking for something stronger than rope.
Which is why alternatives like metal chains came about. Trouble is, compared to rope, metal chain has a nasty way of breaking.
So now I want to test a 10mm metal chain, the same diameter as the rope we snapped. I'm going to film it with a slow-motion camera while using water from a friendly fire crew to gradually increase the weight in a skip.
Are you ready for us to film?
Yeah, carry on. And the load's now starting to go up. so we've got to 800.
Remember, the same size rope broke at just 640 kilos, not even 2/3 of a ton.
Just about to hit 1.7 tons. So now we're hanging a large car from it.
The chain is rated at 2.5 tons, but we've already hit over 3.5 tons, and it's still holding. Now we're running out of water.
We've probably got about a minute's supply.
What you're telling me is our chain is too strong?
Yeah.
Yeah. OK, thank you.
Oh, there you go. Or maybe not.
3,790.
Just like in the mines, the chain takes a much greater load than rope, but it breaks catastrophically and without any warning.
Oh, that's perfect. So that's exactly, it's where the two links cross over, and
That's
it's that
right, yes.
shearing, it's where it's bending it round.
So how quickly were you recording this?
We're recording at 2,000 frames per second.
So that broke in less than 5 milliseconds?
Yes.
So you'd have no warning at all?
It's instant.
Ah, you have the culprit.
We found the link here in the water, and so you can see here where it's failed.
So the significance of this is where it's gone is a weak point inherent to the chain.
It's inherent to the design of the chain that the material here is going to see a shear stress that's going to cause it to fail.
And this shear strain, this bending on it, that's every chain has that weak.
Every chain is going to have that weakness at that point.
And that's what cost lives down the mines.
Exactly, yes.
A failure that catastrophic
Yes.
and that quick. What can you do?
What can you do?
And that's where a great invention for a German silver mine comes in.
In 1829, Herr Wilhelm Albert, director of a Clausthal silver mine, having witnessed chain links snap without warning, was inspired to reconsider the merits of rope.
So what was needed to haul huge loads of silver from deep in the mine was something that combined the structure of rope with the strength of metal. Herr Wilhelm Albert discovered just that. He twisted metal strands together to form a metal rope, the world's first cable.
To prove Wilhelm Albert was onto something, we tested cable. No surprise, we quickly got the skip to overflowing. The cable, although the same diameter as the chain, is easily carrying over 800 kilos more, and well over 4,000 kilos more than the rope. It's the best of both worlds. Twisting metal strands together like rope means cable is exceptionally strong, and when it fails, it should give ample warning, just like rope. And back at Millau, the engineers were utterly confident in the strength of their metal ropes. At one point during construction, almost 170 meters of deck hung over the valley from just 6 cables. The completed bridge is designed to carry 35,000 tons. That's the equivalent of pickup trucks crammed nose to tail in all lanes, piled 10 high.
But there's a neat twist here at Millau. This bridge is designed to last 120 years, but inevitably, a century-old cable isn't as strong as a new one. But if the bridge is held up by cables, how do you take them down to replace them without the bridge falling down? Well, the answer to that lies in the construction of the cables themselves, because from above, they look like a single solid piece. But in fact, each one is made up of a bundle of as many as 91 smaller cables. Here they are. Those smaller cables, in fact, are then each made up of 7 individual strands. And their job is crucial, those middle-sized cables, because each of those can be taken down and replaced if they corrode without having to take down the entire bundle.
Prompted by accidents in German silver mines over 180 years ago, the inspired idea to make rope from metal strands has made the magnificent Millau Bridge possible. But the bridge would still collapse in the scorching summer heat without an engineering solution borrowed from the ancient Celtic boat builders.
Building with metal comes with one massive drawback. The hotter it gets, the more it expands.
Let me show you a little example of metal expansion.
This is a heavy-duty jar, pretty tough to break. This is a metal core. Putting the jar around the core, I shall now apply
heat. And, well, you've probably guessed what's going to happen if I heat up the metal core and expand the metal.
Add heat to metal and it expands. This becomes a problem, though, when the metal is up against a material that's much less flexible, in this case, glass.
And while we're waiting for something to happen, it's worth thinking, where else might we find large amounts of metal interacting with a material that doesn't like to bend?
The tiny expansion in this demonstration scales up the more metal involved. Rail track can dramatically expand in extreme heat, and with nowhere to go, it inconveniently buckles. If this were to happen on a bridge, it could be a disaster.
On your average bridge, you leave gaps, expansion joints, to take up movement of the deck with changes in temperature. But this is not your average bridge.
The Millau Bridge has been welded into one continuous piece of steel from end to end. The only place for expansion gaps is where the road meets the valley at either side. In the heat of summer, these expansion joints have a critical job to do.
Every summer, the bridge is heated up and it expands. The engineers predict that at 40 degrees, it grows by about 1.2 meters. And that's what this section is for, to allow it to do that. The expansion joints above my head, that you can hear the traffic thundering over, allow the road to remain a continuous surface as the bridge moves backwards and forwards on these mounting points. Even the cables taking power to it are designed to be flexible with that movement. And that's all well and good here, where the bridge meets the land. But it doesn't expand just at its ends. It expands all along its length. So what do you do at the points where it's fixed to those concrete piers?
Obviously, the deck has to be fixed to the piers for stability. But in summer heat, the 2.5 kilometers of horizontal deck expand. It's the growth along its length that's the real problem, because it exerts a massive, unstoppable force on the vertical concrete piers. And concrete is notoriously unbendy. So the engineers came up with a very clever solution.
The base of each pier is solid. But the top 90 meters is split into two thin arms.
How does this weird design overcome a potentially fatal threat? That brings us to our final connection: prehistoric Celtic boats. For centuries, the ancient Celtic peoples of Ireland and Wales used ingenious boats called curraghs. They were made of a bent wood frame and covered with hide or sometimes canvas. The key to making concrete flexible enough to withstand summer heat lies in the wooden skeleton of some of these boats. In some curraghs, pieces of wood, including a keel stringer, would run under the boat from stem to stern. They had to be strong, but also had to curve. Even flexible timber can only bend so far, but some early woodworkers found a way around this. To find out how, I'm visiting the carpentry shop of Peter Faulkner, whose passion is building these craft.
Peter.
Richard, hello.
So, you run a workshop here building traditional boats using ancient skills, but there is a link to do with the way the pillars of our bridge are built. It is to do with that split in them, and I think before we can really understand it a bit more, we need to split some wood. How do you do it?
To cleave it, yes?
Yes,
yep.
Cleave, that's the word.
You want to cleave some now?
Yes, I'd like to cleave some wood.
Great, right. A couple of pieces here.
That's a piece of wood.
That's a piece of ash?
Yes.
So we just make a... I'm going to put in a wedge.
Cleave away.
Right. So do you want to have a tap?
Have a tap, yes.
You'll soon work out. Right.
These are not modern tools, are they?
No.
But then I guess this tells us that actually people have known about cleaving wood for a long time. This isn't new technology, is it?
No. Prehistoric. I mean, we don't know, 10, 20,000 years.
Cleaving the wood like this means it splits along its natural grain and keeps its strength. But it also changes the flexibility of the wood dramatically.
Let's imagine this now was one of the pillars supporting our bridge. The problem here, remember, is flexibility, because the road deck is so long. When it gets hot, it expands and it moves out this way, or it shrinks back this way when it gets cold, and that needs flexibility. It'll just snap the pillar. With these splits in it, I mean, this will bend as much as you like, but because we've left the same amount of wood in it, the same amount of stuff, it's still just as strong at holding things up. There's as much to work under compression.
I feel a test coming on, with two pieces of timber exactly the same size.
Right, what I have here is my unique and custom-built flex test rig. This is one of the pillars, OK, represented by this big chunk of wood. And actually, proportionally, it's almost the same as the pillars, width to height.
I'm going to test an uncleaved post first. I've added these straws to measure how far it will bend before it snaps.
What happens to this? If it flexes, it'll start to knock these little straws out. So, using this winch, I will pull on that wire to apply the same force as if the road deck were expanding out this way on top of my giant pillar. Wish me luck. Now we're making our way towards the first of my little pegs. How far will it bend? Oh, we got one. The tension grows as the deck expands. Oh, no, it's all gone wrong. Well, we've hit 3 of the little straws, but, oh, yeah, that's not good at all, is it?
Now, with the new post, Peter uses wedges to drive a split in it. Will this cleaved timber really bend further than the last post?
Right, now, to simulate another hot day at our bridge, the sun comes up and warms 2 kilometres of steel road deck. It expands and pushes our column. That split in the wood is allowing it to flex. It can still support the same weight from above, but it's coping. Right, that's 4. I'm going to see if I can get it back.
So this split timber has gone twice as far without breaking as the first unsplit one. But will it return to its original state? As I release the tension, the wooden test pair shows it handles the stress without any permanent damage.
All of that flexibility given to it just by this split in it, down to there at the top, lets it bend. It can still support, but now it can bend.
Modern woodworkers believe Celtic boat builders use this same principle for their curraghs. The wooden keel stringer could be split to allow it to bend, whilst keeping it strong and sturdy. On the Millau Bridge, concrete, which is usually more like brittle glass, can become more flexible with a split in the right place. I decided to go to the top of one of the concrete piers to find out just how they cope with the deck movement in summer. I wished I hadn't.
The ladder is strong. 4.
Climbing the ladder down onto the tiny inspection platform precariously positioned on the tallest bridge pier on Earth was more than scary. A lot more.
OK, I'm assuming there's somewhere down there to attach the harness to. Oh, that's a view. My, that's a view. Oh! Mother of God. That's fantastic. If I faint, is that an excuse? Oh.
Second time, and I brace myself to face the winds and my fear 245 metres above the Tarn Valley.
OK. Where does this go? Oh, I feel better now.
Bridge engineer Sylvestre Galice explained, as I hung on for dear life, just how the concrete Y shape allows for movement of the pillars.
The Y form on the concrete structure makes the movement easier.
So the pile, if you like, is fixed to the deck. It's the deck that's in charge, and the pillar has to move with the deck as it expands and contracts.
Great engineering, making concrete bendy. But discussing the concept nearly a quarter of a kilometre in the air wasn't my idea of fun.
Thank you very much for explaining it to me. I'm not sure I'm so grateful to you for bringing me here to do it. We could have done this on the ground.
In the roasting heat of high summer, when the massive metal road deck expands, these split piers can flex 10 times more than conventional concrete towers. Then, as night falls, the bridge cools, the deck shrinks, and the giant piers return to shape. Concrete cleaving is just one inspired solution to the many exceptional challenges that the Millau Bridge engineers overcame and rightly celebrated.
They wanted to build a bridge that was more than just a link between the two sides of the valley. They wanted to create a structure that, rather than detract from, would add to the landscape. A sculpture in a region treasured by France for its natural beauty. And for what it's worth, if you ask me, they did it.
Who would guess that to make it they embraced the power of lightning, were guided by submarine navigation, used a chance discovery from a chemistry lab, cables prompted by accidents in a German silver mine, and were inspired by a crafty idea from ancient boat builders. The Millau Bridge, a stunning piece of engineering made with incredible style.